All right, let's start. Today we are going to talk about electric currents. We are going to start a new chapter. Last time we have finished waves, diffraction grating with you, right?
Yes.
And starting from today, we are going to study electricity and then magnetism. You already know a lot of things about electricity from your secondary school, from your last year IGCSE course. You are familiar with electric circuits, current, charge, resistors, simple principles of circuit electricity. We have also learned a little bit about electrostatics last year. This year, in AS Physics, we are going to look at in more detail to complex electric circuits. But before we start electricity, I want to have a kind of general introduction to the chapter. So today we are going to talk more about the applications of electric current in everyday life. Why electricity is very useful and important for us. We are going to answer this question. And after that, we are going to see the link between current, charge, and time. So you will remember what current is, and we are going to express it this time in a mathematical formula. You are going to calculate problems with charge, current, and time. Okay, let's start with this image. When I was preparing this lesson, I was looking for an image to show it at the cover of this lesson, let's say, and I found this actually, and I really liked it. What do you think it is? Is it something different? Do you see something different there? Yeah. What is this symbol for? Usually we use this symbol for electricity, right? It's an electricity symbol, but as you noticed, it is with papers, right? The image is made with papers. It's a clever design, actually. There are pieces of papers. What's to do with papers and electricity? Maybe this could help you. Greenpeace. Yeah? Recycling. Yeah. It says recycle paper, save electricity. Most of us maybe never thought about this, but recycling paper saves a lot of energy, especially electrical energy. In order to produce a piece of paper during the production process until it comes into your hand, there's a lot of electrical energy consumed. Therefore, every single piece of paper actually contributes to the save of electricity. And actually, I have a kind of number here, which says if you recycle 1 ton of paper, you can save about 4,000 kilowatt hours or 14 gigajoules of electricity. And this is enough to power a 3-bedroom European house for an entire year. You don't need to pay anything for the whole house if you just save 1 ton of paper. I mean, it's just the same amount of electrical energy that you have consumed. And it's the same energy, enough energy to heat and air condition a house for almost 6 months, which is actually a reasonable amount. Right, so electricity, when we say electricity, it is all around us. Even the piece of paper that we are using right now is indirectly related with the amount of electricity that we use. I want to show you the objectives of today's lesson. As I said earlier, we want to see the place of electricity in our lives, first of all. I mean, to see some everyday applications and the place of electricity in our life, in our body, in our world around us, I guess maybe you will have some more interest in the subject. And after that, we will look at the electric current and its main definition as the flow of charged particles. We will define current. Then we will define charge and the unit of the current, Coulomb. And at the end here, at the end of this section, we will learn the formula, mathematical equation of Q equals IT to solve some numerical problems. This is our object. Let's write now electric current in your notebooks as the title, right? Electric current. And take your notes about the main sections of this lesson. Take your note. It's all about charged particles. You can just highlight those words. You can just write these words that I'm writing right now and highlighting charge and Coulomb and the equation of Q equals IT. These are the things we are going to learn. But before, as I said, the important place of electricity in our everyday life. Okay. It doesn't happen very frequently actually in Romania, but you know how it feels when the electricity is gone. Blackout. Have you ever felt something like that? For a long time?
Yes.
Huh? When was it?
Last year.
Last year. Where was it?
I think it was summer.
Summer?
Yeah.
And how many hours?
Like a day.
All day. And how many people affected, do you think? All the city? You don't know? What about you?
In Syria.
In Syria?
Yes. Like 2.5 years ago, they used to shut it every day.
Every day?
Every day, like around 4 hours.
And how was it?
It was terrible because it was really warm and there was no air conditioner.
No air conditioner.
Yeah.
In the middle of the summer, no electricity. Lots of things would go wrong, right, in your life. You're right, it is a very terrible thing. And now I'm going to ask you, what is the biggest blackout in the world history? Do you know? The biggest blackout, according to the number of the people affected and the duration, hours of the whole thing, the power outage, no electricity. What was it?
Was it in India?
India. You're right. When was it?
It was when the process of the fuel was failed.
Okay. And at what year it was, do you know? It was actually last year. In India, this person is trying to have an haircut under the candlelight, actually. In India, July 2012, something terrible happened. Because of the blackout, no electricity, traffic lights didn't work. In most of the country, there was no electricity. People just stayed in the middle of the traffic jam for hours. It lasted 2 days. And you know how many people were affected? No trains, no transportation, almost no, some kind of communication also lost. Government couldn't solve the problem urgently, and people waited in the train stations for hours. And it affected 620 million of people. Imagine if it has happening in India, this is something we expect. 620 million people was with no electricity almost for 2 days. And that was terrible. People didn't do their work and life was without electricity. What do you think? Life, how would it be without electricity?
Very hard.
Very hard. What kind of things you wouldn't use? Tell me. Huh?
phone.
No mobile phones. First thing you remember, all the time you're using mobile phones.
TV. Electric heaters.
Heaters, air conditioners as well, right? Like you said.
Fridge.
Fridge, yeah, big problem. All the things you buy should be consumed immediately, otherwise they are all wasted. What else? Mansuri, what's the place of electricity in your life?
Anything from washing, using heating water.
Heating water, right? No hot water at all. Good. What else?
Air conditioning.
Air conditioning, we said already. TV, no fun. Most of things are dependent in our life with electricity, right? And life without electricity would be kind of very hard for us. People were trying to manage, were living normal with no problem before electricity. But today, almost everything somehow, directly or indirectly, connected with electricity, current in our everyday life. So that's the important place, and that's why maybe we need to learn more about it, and we need to learn the limitations of electricity and the safety precautions that we need to consider. Everything has two sides. If you use it well, it has lots of advantages on one side, but if you don't know how to use it on the other side, it might cause a serious problem for you. So we need to learn how electricity works, how it is made, and how it could be used safely. This is important for us. Alright, so we use, like you said, air conditioners, devices, lots of mobile phones, everything. All electric and electronic devices have something common. I want to show you a kind of presentation here about those electronic devices that we are using in our everyday life and what they do, about what they do. Let me try to open that presentation. Okay. In this presentation, I have tried to show you something common in most of electric and electronic devices. They usually take one form of energy and convert it into other forms. Say, a device, for example.
Blow dryer.
Huh?
Blow dryer.
Hair dryer. What?
Hair dryer.
Hair dryer. Okay, what does it do? Hair dryer. What kind of energy does it take?
Electricity.
Electric.
Electrical energy. It takes into and changes into heat. And there's a fan as well, which converts, which takes energy from electricity, converts it into kinetic energy, in that sense. Good. Electronic devices, electronic control systems also have a component called sensor, and those components also work with electricity, and they use a physical stimulus, just like heat, light, sound, pressure, or motion. There is a physical stimulus from outside world, and they change this physical stimulus into an electric signal. So without electricity, all the devices that change electrical energy into other useful forms wouldn't work. And all the sensors mounted with those electric and electronic devices that take the physical stimulus of the outside world from the environment wouldn't be able to convert them into electric signal. These are all happening by the help of electricity. Can you give me an example for a sensor which makes a physical stimulus, turns it into an electric signal? Give me an example. Yeah.
When it's really hot in summer and in the places where you grow crops,
Mm-hmm.
when it's hot, it opens the water.
Water supply, or it opens the window or something like that. In agriculture, right? You mean agriculture? We have some systems which adjust the humidity and the water level of the plants automatically. You're right. They measure the outside temperature using the sensor, changing into an electric signal to an output circuit. They either turn on the heater or The air conditioner, for example. Good idea. What else? Yes? Okay.
A simple alarm.
A simple alarm system works in the same way. What kind of alarm? For example, alarm with sensitive to motion. For example, when somebody enters the room, sensor detects that movement and rings the bell. Good.
The washing machine.
Small detectors, smoke detectors. Yes, they also work in the same way. We can extend the list. We can give lots of examples for that. I want to just show you two examples, simple ones, like electrical energy converted into heat energy when you are using a kettle, an electric device. Or when you have a solar cell, a photovoltaic cell, it changes light energy into electric energy. These are the examples for devices, electric devices. And if you are using a sensor, for example, an image sensor, CCD, in a camera, you just change light into electricity, right? So most of the devices, electric devices, use the same technique, the same method of electronic control system. For example, the microphone converts sound into electrical energy. Right. Tell me another sensor that you use in almost every second of your life. There is one sensor, or there is a set of sensors, let's say, an example that you use all the time. You are dependent on that. You can't live without microphone. You can surely live your life without a camera, but you can't do without that sensor. Yes, think about it.
Brain.
Brain has a kind of sensor. Yes, brain is a part of it actually. But before it goes to your brain,
The heart.
The eyes.
the eyes, yes, they have sensors as well. Actually, we can say in general 5 senses.
The skin.
Seeing, hearing, tasting, touching, smelling. All of these processes, all of these senses are possible to feel, to sense by the help of some sensors. What are those sensors? Let's have a look. Sensors in our body, special receptor cells for each of the senses. We have a special receptor, a sensor, for each of the senses we are using in everyday life. For vision, we have rods and cones in the eye. They are highly sensitive receptors to the contrast and the color of the light. We have different sensory cells for hearing in the ear. Pressure sensors. We have some very interesting and very sensitive sensors to smell. They are working in a chemical process. We have some sensors on our tongue, taste sensors. We have touch sensors. And maybe this is one of the most interesting things actually for me, because when I saw the next photo I will show you, I was kind of surprised. It's just showing a very small section of your finger. Cut a very small part in your hand. Let's say 1 millimeter square of an area from your finger, from your skin. You have different sensors in that small area for different purposes. You have a sensor to feel hot objects, sensitive to heat. You have a sensor, different sensor to feel cold. You have a different sensor for light touch. If you imagine, you can feel a light touch. Or a strong pressure. You don't initiate this sensor until you have a strong pressure. So light pressure and strong pressure, they have 2 different functions. And you have a pain receptors. Without those pain receptors, imagine, you cut yourself, you don't feel anything. You hit yourself, no pain, and you're not aware of what's going on, which would be very difficult. There are some illnesses like that. So every square inch of our body, on our skin, actually is full of sensors. Now, I'm trying to come to a point here. We have sensors in our skin. Sensors convert what? Change the physical stimulus and convert into electrical. Can you now say that our body is a kind of electrical device? Does it work with electricity? Yes, it does. Our body, with lots of functions in it, works with electricity. So without electricity, you wouldn't be able to see this image right now. I wouldn't be able to talk, see, hear. You wouldn't be able to read all of this stuff. You are all working with electricity in your body. Okay. So, that's why I think it's important. Let's go on. We talk about electricity, and of course we have to define currents. Now, please write down the title, Definition of Electric Current. Definition of electric current. We have learned static electricity last year. Today we are going to talk about the next stage, current electricity. It's different than static electricity. They all have something in common with the flow of charge. Electric current, on the other hand, needs a complete circuit, a loop, in order to run. If you have a loop, a closed circuit, such as a flashlight, some wiring system is connected to a battery and to a light bulb. When you turn it on, when you switch it on, bulb is lit, it's on. This is because of some flow of charge in the circuit. And that flow of charge produces a current. This current, people, can be defined as, please write down, as the rate at which the charge flows past a point on a circuit. So I have, let's say, a conductor. Alright? Current can flow only through conductors. Let's say this is a conductor, right? Through a certain point, past a point on a circuit. Actually, this is connected to the outer circuit. It has other parts connected to a battery, for example. Some current flows, we say, through the conductor because there is a charge, Q, that's flowing through the conductor. What are those particles that flow in the conductor? Yeah?
Are they electrons?
Electrons, yes. Electrons actually run in a different way. So, when electrons flow through a conductor, we say there is a current flow. The current direction is defined as the opposite direction to the charge flow, electron flow. We are going to see this later. Because of the invention of the electrons before the current direction defined, we have a kind of conventional current direction. And we just look at one section of the conductor here. When a certain amount of charge flows through a certain area, cross-section area, in a unit time t, we say there is a current. And simply the ratio of the quantity of charge and time. So I can write current as divided by time. Rate of flow of charge. So charge over time is equal to current. Charge over time. I can write this in terms of symbols as I representing current, Q for the charge, and T for the time. And what are the units here?
Amps.
Amperes for the current. Yes. Amperes is the current unit represented with capital A.
Coulomb.
Charge, Coulomb with capital C. Don't confuse this capital C with current. Current, capital C. There's a kind of common mistake. Coulomb is represented with capital C. Current always starts with capital C. It's represented by capital I. And this is time. T is time in seconds. Let's write the equation now. Alright. So 1 amp is equal to what? 1 amp here is equal to
1
1 coulomb
coulomb per second. Per second.
over second. You can write this down as well. 1 amp is equal to 1 coulomb over second. I'm going to give you some questions now. This is our worksheet. We're going to solve some problems about this. Not only for this unit, also for the following units of electricity, we are going to use the same paper. So don't lose it. We are going to use it again. The first question. Yuan,
Yes.
can you tell me which of the following is the base SI unit for electric charge? Ampere,
E.
Coulomb, Ohm,
E.
or volt? Which one?
E.
Coulomb. That's right. Okay. Number 3. We skip number 2. Number 3. It's actually number 1 here. There is a current of 0.24 amps through a lamp for 40 minutes. How much charge passes through the lamp? Can you calculate that? Okay. Calculate
Yeah, wait a second.
the amount of charge passes through the lamp if it has a current of 0.24 amps and running for 40 minutes.
I got 576.
9.6 coulomb.
576 coulombs.
Because you need to change the 40
You need to
minutes.
change that into seconds. Very good. Let's write the, I will give you time, but let's write the given quantities here. It says the current, right? So I is equal to 0.24 amps. For 40 minutes, this is the time, of course. So I have 40 minutes of time. In order to find my answer in coulombs, can I use minutes?
No.
No. I need to convert it into seconds. How many seconds is that? (2,400 seconds. Right? Every minute is 60 seconds. Therefore, applying the formula for charge, current was equal to Q over T. So charge is equal to what? Yes? IT. And remember this equation from quit IT. Maybe you can use that. Quit IT. Q equals IT. Therefore, I is equal to 0.24 amps. Therefore, multiplied with 2,400 seconds, and you get what?
576 coulombs.
Very good. Which option is that?
A.
Coulombs. Alright. I solved the first question. Now it's your turn.
So
Did you write?
yes.
Okay. Next question is about a lightning strike. All right.
So we have
That is question number in your paper 15. Okay. We have a thunderstorm. Lightning is a form of electricity, isn't it?
Yeah.
You remember the Benjamin Franklin's experiment
Yeah. With okay.
with the kite and a metal key? He was able to conduct electricity from lightning to the ground. Hopefully he didn't die, but the next scientist who tried the same thing actually died, unfortunately. Because it's a very big amount of electric shock if you are exposed to that. So never try it. 9,000 amps of current, imagine that. It has a current of 9,000 amps. No surprise that he died, because it's a very big amount of current. And this transfers a charge of 18 coulombs to the ground. When it strikes the ground, it transfers 18 coulombs. Can look like a very small number, but we are going to see the number of electrons transferred, and you will see how big it is. Calculate first the duration of the lightning strike. First, we are going to calculate the time. Who wants to do this one? Oh, okay. On the board. There's the question there, you can do it.
I need to use this value to find the
Yes,
total.
you can use that one. Current equals charge over time. We can put that, okay. You can place that equivalent sign here, right? Okay. 9,000 amps. You got it? You said X? Okay. I will prefer T as a symbol. Just write T. Okay. Here also. No need to write. Okay. T equals 18 coulombs divided by 9,000, and it's a short time, isn't it? Lightning strikes in a very short time interval actually, which is 2 times 10 to the power of minus 3 seconds. Thank you very much. That's right, I guess.
Yes.
Did you get the same thing?
Yeah.
How many milliseconds is that?
2 milliseconds.
2 milliseconds only. It takes only 2 milliseconds of time to deliver this amount of charge with this amount of current. Okay, now B. How many electrons did we transfer? Yeah,
18.
how did you get that?
No, from one electron carries 1.6 times 10 to the power of minus 19 coulomb.
That's
So we
right.
use the ratio to find the number of electrons.
Okay, let me try to write down here. One electron, that's part B, has a charge of, please write this down, 1.6 times 10 to the power of minus 19 coulombs. If this is the charge of one electron, and we have total charge of 18 coulombs, how many number of electrons we have? Let me represent it with N.
It's 18 over 1.6 times 10 to the power.
Exactly. So, like Tuba said, we have total number of charge divided by the charge of one electron. Alright, let me represent that with E. Total charge divided by charge of one electron will give you the number of electrons. So number of electrons will be 18 coulombs divided by 1.6 times 10 to the power of minus 19 coulombs. And how much do you get?
1.125 times 10 to the power of 20
Okay, does it have unit?
electrons.
It's electrons, yeah? It doesn't have any unit. So this is a very big number actually, right? 11.3 times 10 to the power of 19. Too much. Billions of, millions of, millions of, billions of electrons actually. And this amount of electrons will be transferred to the ground by this lightning strike. Any question?
What is N number?
N is the number of electrons. Okay. We have a graph question, the last example here. There's a graph question, number 18. Have a look. Number 18. A cell provides a constant current to the circuit. Diagram shows the graph against time. You have a current time graph, okay? Calculate the flow of charge in a time t when the current is I. It's simple, the calculation. Nisa, what's the calculation here? The area under the IT graph. Very good. Okay. Howji? The area under the graph gives you the charge, right? If you look at this graph, if this is true, look at the graph and estimate the total charge delivered. What can you say?
600.
Huh? What can you say to find the total amount of charge in the graph here? How can we find the area? Can you find the area? Okay, go.
It's 750
You want to do it here or there? We have 1.2 amps and total 650 seconds. Right?
750. How much?
750.
Write Q first of all. Q total charge is equal to that. Okay, you didn't write the units, but at least say at the end that's coulombs. Okay, your friend wrote a very long actually mathematical equation. Can you please explain how you get that? 1.2 times 600? It's the area of this rectangle and the area of this triangle. You said 1 over 2 times 1.2 the height and 50 is the base. Very good. What's the result?
700.
750? 750. No, 750. 750. 750, man. Okay. So not 7 million. Okay, all right. Thank you. But you did well. You did the calculation well. You didn't write the result well. All right. 750 coulombs.
750.
750. Okay. So that is the total chart, whenever you have IT graph, please find the total area. Total area. You could also find from the area of trapezium, right? Large base plus short base times height over 2. By the way, be careful if you calculate the triangle area. This is only 50 seconds. And the height is here 1.2 amps. Okay, good. I guess you got the idea. Let's do something interesting now. Before we do something interesting, I have to talk about this. Charge carriers. We don't always have electrons in a circuit that flows to produce current. What else they might be?
Charge.
What charge carriers?
The
Ions. Very good. What could be the possible charge of ions? Positive or negative, right? Yuan? Can you tell me the charge of an electron? First case? There can be some electrons, right? Carrying the charge. What is the charge of an electron? What, minus or plus?
Mine.
Come on. Minus. Very good. If the charge of an electron is negative, they flow in a circuit from the negative terminal to the positive terminal. But in that case, the conventional current direction, here's the story of that, why it's different, is in the other way around, just like the way I told you before. So if the electrons move, let's say, this way, the conventional current direction is in the opposite way, like this. Second case, second scenario, the positively charged particles, let's say, flowing, they are like positive ions, or even, like in CERN laboratories, protons, positive particles, positively charged particles, like ions. If they move in this direction, the conventional current direction is also the same. So conventional current direction is always in the same direction with the charge that is positive flowing in the circuit.
So the charge is not always electrons. It can
No,
be positive.
charge can be proton, charge can be a positive ion, charge can be even, in the third case, both. How could this be possible?
Alternate.
There could be some cases both positive and negative ions move. Yeah?
Electrolysis.
Electrolysis. Very good. If you make an electrolysis experiment in chemistry, you know that. So it can be either of them. Alright? This is a case where we have the... So charge carriers, positive or negative, they could be both producing the current in the circuit. And you know what? Your brain sends the electric signals by those positive ions actually. So it's not always electrons. There is a myth saying that we only use 10% of our brain. Do you know this character?
Yes.
Alright, yeah. And some of us probably use less, but it's a myth. It's not correct actually. And the human brain with thousands of millions of neuron cells actually communicate with each other by using those ions. There is a whole electric circuit in our brain doing this. So we are going to talk about how neurons transmit electric signals next time. And I'm going to show you a very interesting video. But your homework, let me tell your homework, page number 204, questions 3 to 7 is your homework. Please write it down before you go. Alright? Yeah? And have a nice day. Thank you.